Okay, so today is the last class, and we will talk about Hager diagrams, Kirby diagrams, and maybe a little bit about the Cobordism theorem. So let's start with Hager diagrams. So Hager diagrams is basically trying to understand what we get from handle attachments for three-dimensional manifolds. And they only really work well for orientable manifolds. So we won't talk about non-orientable three manifolds. So suppose X is a closed, connected, and orientable three manifold. So we want to see, basically, we want to break it up into handles and kind of understand everything that could happen. So first of all, we can consider a Morse function with unique index 0 and 3 critical points. So, that means I can always construct my three manifold using a unique unique 0 handle and a unique 3 handle. So I explained this last time, how you can do that. So basically, all the complexity lies in the 1 handles and the 2 handles. Okay, so then we have, say, P1 through Pm are the index 1 critical points. And you have Q1 through QR are the index 2 critical points. And I showed you last time that you can actually lift up and down the value of the function. So we could assume that the value of the function, all the critical values corresponding to index 1 critical points are strictly smaller than all the critical values corresponding to index 2 critical points. And you can actually, just to make the things, make it even easier, you can make them all equal. So you can make the value of the function in the index 1 critical points be the same, be equal 1, for example. This is something a little funny, but that's done in the literature. This is called the self-indexing Morse function. So we can assume f is self-indexing. So, if this is my manifold, my three manifold, then this is my Morse function. Then the maximum is attained at the level 3. The minimum is attained at the level 2, at the level 0. And all the index 1 critical points are attained level 1. And all the index 2 critical points are attained at level 2. This seems a little silly, but why not? And basically, this comes from the fact that we can these 1 handles, they attach separately from each other. We can always kind of perturb them away so they don't interact with each other. So we might as well attach them all at the same time. Okay, so let's see what happens when we attach 1 handles. Okay, so a 0 handle, we've already seen this. A 0 handle is just a B3 attached to nothing. So it's just something like this. So what's a 1 handle? A 1 handle is a B1 times B2 attached along S0 times B2. So what I have to do is I have to choose an S0 on my 0 handle. So I have my 0 handle. I have to choose an S0, so I have to choose 2 points. Then I have to thicken it to a ball. Each of them I have to thicken to a ball. And then I glue my, and I glue this 1 handle. And you can see basically that there's up to the diffeomorphism type of what you obtain at the end, there are only 2 different framings. So basically you have these 2 balls, these 2 little discs, and you can either choose them to have the same orientation, or you can choose them to have the opposite orientation to each other. So it's very analogous to attaching 1 handle to a surface. You have sort of the orientable one and the non-orientable one. So I don't want to worry about the non-orientable three manifolds. So basically, if I want this end result to be orientable, then there's a unique framing. So there's basically, once I choose my S0, there's a unique way to glue a one handle. Okay, so supposing orientability, there is a unique way to attach a one handle. And in fact, if I attach M one handles, so after attaching M one handles, what you get is basically you get a ball like this, and then you have just M of these one handles. Okay, and up to isotopy, there's a unique way to do that. You can always like slide these handles and to make them have the standard whatever this picture you want. So what you get after attaching M handles is you get a compact three manifold, which is, if you want, you can take an embedding, a beautiful embedding of the genus M surface, and you take the interior of it in R3. So this, I'm going to call this HM. So this is the interior of this standard embedding, or the closed interior of the standard embedding of the genus M surface into R3. Okay. When I say closed interior, I mean interior in the sense of the Jordan curve separation theorem. So you have this standard embedding of the genus M surface into R3, and then you have the inside and the outside. So you just take the inside, the closure of the inside. I think it's pretty clear what I'm trying to do. Okay, so for M equals 1, you have what's called the solid torus, but for higher M, it is like the solid genus M surface. Okay. Any questions about this? Okay, so now I have to attach the two handles. So how do I attach a two handle? So now I have two handles. So how do I attach two handles? Well, a two handle is a B2 times B1 attached along an S2 times a B1. Sorry, an S1 times a B1. So now I look at my genus M surface, and I have to find a circle inside of it. So once I find a circle inside of it, I have to thicken it, and there's a unique way to do that to keep the orientability. And then I just glue this two handle. So say my two handle now is going to be so I just glue this guy. Okay, so I have to do that a number of times. So I have to do that, what was my number? R times. And then I hope that by some miracle, I end up so now I have to end up with a compact three manifold such that the boundary, whose boundary is the sphere. Because after the two handles, now I have to attach a three handle, which is a ball, along this S2, and that have to be done. I have to have a closed manifold. So basically, this means that there is some restriction on how you add these circles. Like if you just add one circle to this, in this case, for example, this is not going to give you what I drew here with where m is very high, and I put an r equals 1. This is not going to give me something whose boundary is S2. So there is some restriction on these R embeddings. Okay, so let me tell you what this restriction is. So first of all, there is kind of an easy thing that you can see, which is the following. So say that, you know, we have, let's kind of draw this thing schematically. So we have a 0 handle, and then we have M1 handles. So this, sorry, my picture is a little funny. Okay, and then I have R, 2 handles. And then I have 1 0 handle, 1 3 handle. I have 1 0 handle, and I have 1 3 handle. So now I have these R2 handles that I'm not going to draw, and then I have this 3 handle, which is this ball. But the thing that's kind of amazing is that I can actually, so I know that if I stop here, I have some interior of a genus G surface. I have this N M. But then on the other hand, I can flip my Morse function and think about attaching handles from top to bottom. So if I flip my Morse function, that's equivalent of actually thinking about attaching handles from the top to the bottom. So like now I can start with my 3 handle, and I kind of think of it as a 0 handle. And then my 2 handle, I think of it as a 1 handle attached to the 3 handle. So that means that my 2 handle now is going to be something like this. It's going to attach to the 3 handle. So what this is saying is actually, you know, this by this procedure, when I actually look at this, when I actually look at the manifold that's above this level here, I mean, maybe take this level to be 3/2. What I actually have is I also have this what's called this handle body, but now the genus is R because I attach Rn handles. And the level 3/2 is going to be, you know, just the boundary of this guy, so it's going to be the genus M surface, but it's also the genus R surface. So basically, this implies that M has to be equal to R. Okay, so the number of 1 handles has to be the same as the number of 2 handles. Okay, so that's one interesting requirement. And another way to see this is just using Euler Characteristic, because the Euler Characteristic is going to be the alternating sum of the number of handles. And the Euler Characteristic of a 3 manifold is always 0. So you have that 1 minus n plus r minus 1 is 0. But I think this way is kind of, it's more interesting because it just uses handle attachments. So this is the first condition. You have to have as many 1 handles as you have 2 handles. So now we can say, well, we have our genus M surface. So this corresponds to the genus M. And then if I want to attach 2 handles, I have to add basically M circles. I have to add M circles. I can assume, you know, they don't intersect, so they, you know, it's an embedding of M circles into this genus M surface. And there is another condition which basically, it's similar to the condition that we had for surfaces where, you know, you can't just attach 1 handles arbitrarily and hope that it's going to be closed, but they need it to be intertwined. Here, the condition that you need is that you need that after you cut along the surface along these M circles, you end up with a disk. So what you need is that, like, cutting the sigma M along the M circles, we obtain a disk. So for example, like if you have a torus, it's very easy because you can just take anything, any circle. That's non-trivial in homology. So if I take a circle like that, when I cut it up over here, that's the same thing as what happens if I thicken this up. Then I have, sorry, not a disk. I have to be contractible. Yeah. Cutting along the M circles gives rise to contractible surface. Okay, so here, when you cut along the circle, you end up with basically a cylinder. No, sorry, not contractible. What am I trying to say? I think just connected, actually. Anyway, what you can't do, for example, so this you can do. What you can't do is take like a little circle like this. That's not going to work. Because when you attach a two handle to this, then you're not going to end up with something whose boundary is S2. You're going to end up with something whose boundary is disconnected. It's going to be two S2s. Okay, so you can't do this. This one is not allowed. Basically, I think the right way to say this, or a more a more homological way to say this, I think, I'm not sure if this is really the right condition, but the right condition is that if you take the M circles, they have to be linearly independent in the homology of the surface. Okay, so anyway, if you have a condition like that, then that's enough to determine the whole manifold. So basically, what you need is you need to take a, so how do you construct? How do we construct orientable three manifolds in general? So we have to first fix a genus. So we fix G. So this is a number from 0, 1, and this is going to be the number of one handles and number of two handles. Then we look at sigma G, and we basically have to choose M or G closed curves on sigma G that are linearly independent, are independent. Okay, and that's going to determine, and this determines a three manifold. Another way to think about this is actually choosing these G curves is the same basically as choosing a diffeomorphism from sigma G to sigma G. So because this is kind of a slightly different perspective, but it's completely equivalent, which is to think that if my three manifold, let me draw it like this. So this part here is a genus G handle body. So this is this three manifold whose boundary is sigma G. So this has the boundary is sigma G. And if you look at the stop part, it's also the same thing. So what you need to know is how the sigma G here glues to the sigma G here. This is actually the original approach of Hager. So Hager said, basically every three manifold you can write as the union of two genus G handle bodies. So this NG union with NG, but you glue it along a diffeomorphism of the surface, the diffeomorphism of the genus G surface. Okay, and this, choosing a diffeomorphism of the surface is kind of the same as choosing closed curves. So, basically, a diffeomorphism of the surface is determined up to isotopy by the image of, say, if you take these curves like this, and you look at their image, that determines the phi up to isotopy. Okay, so this is the Hager decomposition. And there was another way, which just basically, yeah. Well, let me leave it like this for now. Are there any questions?
Isso funciona para qualquer dimensão ímpar?
Não. Só dimensão 3. Tá?
Não, talvez não exatamente assim, mas tipo, usar menos a função para classificar só a metade das handles, ou algo parecido.
Você pode falar, por exemplo, que você pode cortar a variedade no meio, né? Você pode colocar metade das alças e depois a outra metade, ela sempre pode separar a variedade, você vai ter uma união de duas variedades. Mas, por exemplo, se você tiver em dimensão 5, né, você vai ter as 1 alças, uma 0 alça, as 1 alças, as 2 alças, as 3 alças, as 4 alças e as 5 alças. E aí, né, você pode cortar a variedade no meio, se você quiser. Você pode falar, de uma certa forma, existe uma complexidade aqui, o nível de complexidade é o mesmo aqui e aqui. Mas essas duas coisas não vão ter mais nenhuma interação, né? Você vai ter 5 variedades com fronteira que se colam, mas você não sabe muito sobre elas, em geral. Dá para falar mais, mas é muito mais complicado, né, do que no caso de dimensão 3. Você não pode, por exemplo, falar que o número de pontos críticos de índice 1 vai coincidir com o número de pontos críticos de índice 4 mais. Né? Não tem mais essa relação. Beleza? Entendeu?
Sim.
Tá. Okay, so let's now go to the world of four manifolds a little bit. Unless someone else has a question about the Hager.
Yes, sir. Would you please explain the function phi one more time from NG union NG?
Yeah, no, so phi is a function from sigma g to sigma g. This is an orientation reversing the diffeomorphism. It's the function that identifies this to this. I mean, it's basically that this. So if you look at the pre-image of 0, 3/2, this is a 0 handle union G1 handles. So this is what we called NG. And we also know that the pre-image from 3/2 to 1, this is also a 0 handle. No, it's a 3 handle union G1 handles. But as I told you, if you just flip the manifold upside down, you can think of it as exactly as G handles attached to a 0 handle. So this is also an NG. Okay. I mean, this is diffeomorphic to NG. So if you want, this pre-image of 3/2 is the boundary of NG, or is a manifold that's diffeomorphic to sigma G.
Okay.
But this is the boundary here, and this is the boundary here.
Yes.
So the diffeomorphism is basically what happens when you fix one of these to be sigma G, sigma G to be the boundary of one of these, and then you look at sigma G as the boundary of the other one.
Okay.
So it's basically looking at these diffeomorphisms here. So if you want, you look at sigma g, maybe the map, if you want to be very precise, is, so you look at sigma g as contained here, and then you look at this diffeomorphism,
Okay.
and then you look at this diffeomorphism here. So you compose this diffeomorphism with this diffeomorphism restricted to the boundary.
Okay.
And that's going to give a map phi from sigma g to sigma g.
Okay. Okay. I understood.
Okay,
Yes. Thank you.
you're welcome. Okay, other questions about this Hager diagram?
Eu tenho uma pergunta.
Sim.
Eu não entendi quando você começa a anexar em alças, por que essa superfície vira um G toro sólido? Ela não pode virar uma coisa mais complexa do que isso?
Não. Porque você está
Certo.
escolhendo. Se você supõe que ela é orientável, né? Não, porque você está escolhendo uma sequência de uma série de S0s, né? Então aqui está o primeiro S0, aqui está o segundo S0, aqui está o terceiro S0, e assim por diante. E só tem uma forma de você fazer o thickening, né? Você engrossar esses S0s, ou seja, só tem uma única forma de você anexar a alça, uma vez que você escolhe o S0. E a menos isotopia, a única coisa que classifica isso daqui é o número de alças. Porque se você tem uma união de MS0, de mergulhos de MS0s em S2, isso aqui, todos são equivalentes, a menos isotopia.
Ah, tá. Entendi. Obrigado.
De nada. Por uma questão de dimensão, sei lá, de transversalidade. Qualquer caminho você pode perturbar para longe do S0. Okay. Any other questions about this Hager decomposition? You can ask me in the middle, so you can interrupt when I'm in the middle of explaining something. Okay, so let's talk about dimension 4. So in dimension 4, we have these things called Kirby diagrams. So let's see how we attach handles. So if we start with dimension, so you start with a unique zero handle. So what's a zero handle? Dimension 4 is just a B4. So it's already starting to get a little hard to draw because we can't draw B4. But it doesn't matter that we can't draw B4 because what we need to do is we need to just know how one handle is attached to it. So what is a one handle? Well, a one handle is a B1 times a B3 attached along an S0 times a B3. So all I need to do is that basically I have to choose 2 points in the boundary of B4. So the boundary of B4 is S3, which we can think of as R3 with a point at infinity. So we can just take everything to miss the point at infinity, and we can just look at in R3. So now I have to, a one handle is just an attachment. I just have to think about 2 points, and then you thicken it to B3. So actually attaching one handles is pretty simple, at least to draw a diagram of it. I can just draw a B3 like this. So when I attach the one handle, basically I remove the interior of these balls, and I think that I have to think that I have this 4-dimensional one handle that glues this ball to this ball. And similarly to how I did it for surfaces, I can think that, I can make this one handle really small. So basically I just think as I enter, it's almost like this point is identified with this point. And this point is identified with this point, and so on. They're not exactly identified. There is a thickening in the middle, but it's almost like they're identified. Okay, so if I have a number of one handles, I can think about just, so here's my attaching one handles. I just have, so here's the first one handle. Here's the second one handle. And just as here, I can up to an isotopy, I can line them up and have them be some kind of standard attachment of one handles. And then I have, I don't know, say this. Okay, so this is what happens. This is my description of attaching one handle. So topologically, there is nothing interesting. It's just the number of one handles. And it's going to get really interesting when I attach two handles. Okay, so is it clear so far, my description? So I'm describing what is a zero handle with a bunch of one handles attached. Okay, so I have one handle, one handle for each of these pairs of spheres. Okay, so now I have to attach a two handle. Again, I'm assuming, I forgot to say that, I'm assuming that X is closed, connected, and orientable. So now it's where things get interesting. So what is a two handle? A two handle is a B2 times B2 that's attached along an S1 times B2. So what I have to do is I have to choose embeddings of S1 and I have to thicken them. So now I have to choose embeddings of S1. So I can, for example, I don't know, I can do something like this. I can do something more interesting, which is something like this. And then here I travel along the one handle. I can do this, and I can travel like this. You see, it really starts to become interesting. Actually, this is topologically, I think, very interesting. I can draw, I don't know, a trefoil. I don't know. So you see that there's a lot of complexity here already. I can do, basically all the things that I can do with knot theory. I can, start embedding knots. And each of these knots will correspond to attaching a two handle. But it's actually more. It's not just choosing a knot. I have to choose the framing as well. Because I have to tell you how to thicken this two handles. So thickening two handles is the same as choosing a framing of a knot. So choosing a basis, just one is enough. So I'm going to have to choose a framing. So choosing a framing of a knot is the same as choosing another knot in the neighborhood. So I can do something trivial, or I can do something that's not trivial, that wraps around. So you see, this is the kind of crazy complexity of two handles. And then you can ask, well, can I actually do anything like that? And then I have to worry about three handles, and I have to close up. And then there's a theorem, which I don't know if it was by Kirby or by someone right before him, but the theorem is that no matter which two handles I choose, there is a unique way to attach three handles so that this will end up with a ball at the end, and so that you can cap with a four handle. So for each such diagram, there is a unique way to attach three handles to end up with a handle body whose boundary is S3. So that's what you need to be able to cap And then when you have that, then you can just put a 4 handle and finish. Okay, so of course this theorem, is hard and there's no way we can prove it here right now. But I guess the point, what I wanted to tell you, is that you can describe any 4 manifold with a diagram like this. Okay? Is this clear? And this is what's called a Kirby diagram. And what Kirby also realized is basically he interpreted handle slides and isotopies and handle cancellations in these diagrams. And these modifications that come from handle slides and handle cancellations are what are called Kirby moves. So you can do what's called Kirby calculus and take one of these diagrams and make it into another one. And you can actually do more. Like this is something, very, very interesting. Is actually if you're given, you can actually cancel all of the 1 handles and end up with a diagram with only 2 handles. Yeah. So that's another thing, like that's another stepping stone of low-dimensional topology. Ok.
Mas você cancelaria mediante qual operação? Não sei.
Existe uma forma de basicamente você adicionar mais, é uma operação mais complicada, mas você pode adicionar outras 2 e 3 alças para cancelar as 1 alça.
Certo, entendi.
Entendeu? Basicamente, para cancelar, né, você pode criar um par de pontos críticos. Existe um fluxo entre esse ponto crítico de índice 2 para um ponto crítico de índice 1. Então você pode tentar criar um par de pontos críticos de índice 2 e 3, tal que o de 2 cancela o de 1. Okay, so any other questions about these Kirby diagrams? Okay, let me then just say a few words about the Ponca Reconjecture and the Cobordism Theorem. So let me remind you, you've probably heard about this, the Poincare Conjecture. Initially, it was stated in dimension 3. It actually turned out to be very hard in dimension 3. So it was stated like this. So say that Y is a closed manifold, 3-dimensional manifold that's closed and connected. And suppose that the fundamental group is trivial. Then Y is homeomorphic or diffeomorphic to S3. I think that was the original statement. I don't know exactly if he conjectured homeomorphically or diffeomorphically. But anyway, this was not proved. But what Poincare proved, I think it was an intermediate step. So I think it's not so hard to prove that if that pi1 equals 0, implies that Y is homotopy equivalent to S3. So homotopy equivalent means that there exists a map from Y to S3, and there exists a map from S3 to y such that the composition of these maps are homotopic to the identity. That's what it means to be homotopy equivalent. And then, of course, the hard part is that it's to show that if this is homotopy equivalent to S3, then it's diffeomorphic or homeomorphic to S3. And it was shown later that homeomorphic to S3 is equivalent to diffeomorphic to S3. So the really hard part is this part. Okay, and then, he tried to conjecture the same thing in higher dimensions, I think, and then he realized that already that it was possible to find simply connected manifolds that were not homotopy equivalent to spheres in higher dimensions. So the conjecture became, if you have an n-dimensional closed and connected manifold such that it's homotopy equivalent to Sn, then Y is homeomorphic to Sn. Also, it was found later that it's possible to have manifolds that are homeomorphic to Sn, but that are not diffeomorphic. So then the meaningful conjecture is this. And it was proven by Smale for n greater than or equal to 5, using what I'm going to talk about in a moment, so using the Cobordism theorem. So for dimension n equals 4, this was proven by Friedman using completely different techniques. And he got a Fields Medal for it. And for n equals 3, it was proven by Perlman much later and using completely different techniques. So this would using Riemannian geometry, using the Ricci flow. And this was, using much older, but also very different techniques. But anyway, what I want to talk about is the case where n is bigger than or equal to 5, because it's the case where Smale basically just uses a Morse theory. And Morse theory in a little bit more. But it kind of comes from Morse theory. So what's the idea? The idea is if you want to prove something is homeomorphic to Sn, all that you need to do is you need to find a Morse function with exactly 2 critical points. So maybe I should say this is a proposition. So if y has a Morse function, so suppose that y is a closed connected manifold, and f is a Morse function with only 2 critical points, then y is homeomorphic to Sn. Okay, so how do we prove this? It's not very hard. This is pretty simple. We know that a Morse function on a closed manifold has to have at least 2 critical points because you have a minimum and a maximum, and the function can't be constant. Yeah, so, but this is the converse of this question, or it's if you have exactly 2 critical points, then you have to be homeomorphic to Sn. And why is that? Well, if you look at a neighborhood of the minimum, I'm just going to draw it by a picture and prove it by picture. So a neighborhood of the minimum, so you basically have a 0 handle. And then a neighborhood of the maximum, you have an n handle. So basically this is saying that y has only a 0 handle and an n handle, and they have to attach. So how do you attach it? Basically you attach it by a map from Sn-1 to Sn-1. This is a diffeomorphism. Okay, so when you attach a map, so basically this is saying that y is the union of 2 balls attached by a diffeomorphism. So now, basically what you have to see is that this, any such a thing, is homeomorphic to Sn. So what you do is you just take this phi and you extend it all the way to the ball. So, basically say that, you have, you know how to glue phi to this, and then basically what you have to do is you have to extend to be able to glue the whole disk to here. Okay, so you have to extend this map phi to the interior of this guy to be able to actually glue Bn, to find a map from the whole Sn. Okay, so Sn is Bn union Bn with the identity map. Okay, so I mean this is an easy detail to fill. We're kind of running out of time, so let me just skip this part. But basically, you have to prove that there's a homeomorphism from here to here. You have to extend this phi all the way to the interior of the ball, and you can always do that, except that at the origin you might have a non-smooth point. That's why you don't get a diffeomorphism, you get a homeomorphism. Okay. And if n is sufficiently small, then this is actually, you can choose it to be a diffeomorphism. So if n equals 2 or 3, I think that, yeah, this can be chosen to be a diffeomorphism. But if n is bigger, then it's not true. And there are counterexamples to that. Okay, so you see that, for example, Morse functions do not differentiate between different smooth structures on Sn in general. Okay, but that's fine. We're not hoping for diffeomorphism anyway, because we know this is not going to be possible. Okay, so how do you adapt this to the setting that we have? So the setting that we have is for the Ponca Reconjecture is y is just homotopy equivalent to Sn. So how do you try to interpret that in terms of a Morse function? Well, it's a little hard and it uses a lot of algebraic topology, but let me just give a hint. So what you do is you remove two balls from y. So basically what you're trying to do is saying, if I remove two balls, then I want to have something that's trivial, that's like a product. So if you remove two balls, from y, what you end up with is you end up with some w. So say w is y minus the union of two balls. And what happens is if you look at the boundary, so the boundary of w is going to be sort of the union of two Sn minus 1s. And so we can think of this W as a cobordism between Sy minus 1 and Sn minus 1. And this condition, this homotopy equivalence, is equivalent to saying that the homology of W with respect to either one of these Sn minus 1s is 0. Which is the same as saying that Sn minus 1, the embedding of Sn minus 1 into W is a homotopy equivalence. Anyway, so there are a bunch of conditions, algebraic topology conditions that are outside the scope of this course. But let me just state the Cobordism theorem. Cobordism theorem says the following. So suppose W is a cobordism between x1 and x2. That just means the boundary of W is the union of x1 and x2. such that it's simply connected, so pi1 of w is 0. And we have this condition that the inclusion of x1 as a boundary and x2 as a boundary, these are homotopy equivalences. So this is related to this condition here. So suppose that the dimension of w is bigger than or equal to 6. Then the conclusion is that w has to be trivial. W is isomorphic. It's a trivial cobordism, so it's some y times 0, 1. So this is going to imply, that x1 is homeomorphic to x2. Okay, so let me just say a few words about the proof of this theorem. So I mean, the idea is basically if you have a cobordism from x1 to x2, then kind of you think of a Morse function. The boundary has two connected components. You can think of one as being the minimum of the function and the other one as being the maximum of the function. And then in principle, you could have some topology and you can have a bunch of critical points. But the idea of the H-Cobordism theorem is to cancel all the critical points. So, and of course you can't do that in general, but if you have these assumptions, then you can. And it's a long process, but the key elements are the cancellation theorem, that I had last time, basically said if you have a unique flow line from a critical point to another critical point, then you can cancel those two critical points. But you have to think about a homological version of it. And that's kind of the crux of the thing, which is, so if you have more than one critical flow line between 2 points, you can talk about positive or negative flow lines. That corresponds to when you intersect, when you look at a level and you intersect the descending and the ascending manifolds, so they intersect at, they have to intersect at a finite number of points by transversality, but these intersections can be positive or negative. So you can count them with signs. So if the sign count is still plus or minus 1, so you have basically 1 with the sign counts, then you can still cancel them. And this is kind of the most important thing. So basically, if you have a pair of intersections, one is positive and the other is negative, then these two, you can get rid of them using something called a Whitney move. And this is the part where you need to have dimension greater than or equal to 6. Okay, so if you have dimension greater than or equal to 6, then you will be able to cancel out, to find some way to cancel out these two, so that you end up with exactly just one flow line, which you can cancel using the cancellation theorem from last class. That's kind of the most important part. There are a few things that also come, which is that these Whitney moves cannot be done with 1 handles and n-1 handles. So first you have to find ways to increase the number of handles in the middle and getting rid of 1 handles and n-1 handles, and then you apply these Whitney moves. But anyway, the point is that you need to have dimensions sufficiently big to be able to do this this procedure, these Whitney moves. You need some space to move things around. Okay, and that's why you need the dimension of the dimension to be bigger than or equal to 5. And actually, we also need a version of the Cobordism theorem where the dimension of W is equal to 5 for the case of a 5-dimensional manifold. So there's a little tweak to take care of that. But anyway, this is beyond the scope of this course, but I just wanted to give you a flavor for those of you who are interested. Okay, so let's finish here. And this is also the end of the class, of the course. So thank you for participating.